Okay, hello. We are José and CHAOUKI, and today we are going to explore voice-based authentication systems. So this research is the continuation of what we did about finding ways to interact with voice command interpreters. So last year we presented some proof of concepts about some ways to interact with voice commands interface without the user knowing it or noticing it. And we thought that the voice recognition or voice authentication would be a good countermeasure against our proof of concept attack. So we decided to explore this world. It's not our specialty, so we had to discover all this environment. And we will propose today the methodology that we followed to explore some voice authentication systems that are deployed mostly in smartphones. So we are CHAOUKI and José. We work with the French French Network Information Security Agency. And we evolve in the wireless security lab. We work on many topics, but our main focus is what we call electromagnetic security. Sorry. So our agenda for today, first we will remind some basics about voice command interfaces, and then we will briefly present the biometrics ecosystem, and especially the voice and the different features of using the voice as a biometrics authentication factor. Then we will explain some metrics that allow to model the voice system, and we will present the tests that we run on several targets. So voice command interpreters are more and more widespread. One can find them in many different devices, especially smartphones, smart home management gadgets, in cars, and also in a lot of kind of IoT devices which don't possess other user interfaces, such as a screen or touch screen. The main editors of such solutions are Apple with Siri, Google with the Google Now or the Google Assistant, Samsung with the S-Voice, which is based on nuanced technology. And what you can do with the voice command interface can vary according to the target and the context. But what we noticed since we started to focus on this interface is that the scope of the commands that are available is getting wider, and the number of critical commands that are available is not decreasing. Today we are going to consider the scenarios where it is possible to get an unauthorized use of this interface, and there have been some public articles about incidents or tricks using the voice interface without the user's consent. Two years ago, already in Hack in Paris, we proposed the technique to remotely and silently induce an audio signal into the headphones of the smartphones in order to be able to execute voice commands without the user's consent. And last year, we presented an extension of that, a continuation of that technique with conducted coupling, so an attack realized from the power network. There have been other propositions in the literature about this subject. Some researchers propose to directly trigger the voice command interface from the phone through a malicious application. In that case, the user can hear the commands while they are played through the phone speaker, and they get executed by the voice command interface. The second proposition was to use mangled or obfuscated commands so that they are not understandable by the user, but they are still recognized by the speech recognition system. So that's a really clever research. And last year, they presented an extension of that work with a lot of improvements. They called it hidden voice commands, and their proof of concept consisted in embedded those commands in YouTube videos. And when you play the videos, you don't notice that voice commands are played, but your phone does. That's a very interesting research. About the security impacts of an unauthorized use of the voice interface, we already presented those last year. It didn't really change. We thought about tracking the user by activating the wireless communication interfaces without his consent. Eavesdropping consisted in placing a phone call to an eavesdropper's phone in order to be able to record or listen to the environment. Cost abuse is to place phone calls or send text messages and so on. Reputation or phishing, using the capabilities of posting on social networks, or sending emails or text messages. And then we considered some scenarios where you could combine different kind of exploits to further compromise the target, such as activating the wireless interface, mounting a fake access point, and then serving a web page, and forcing the victim's phone to visit that web page by issuing a voice command. And of course, with the extension of the commands available through this interface, one could think of a lot of other impacts depending on the applications and the services that are connected to the interface. One of the examples of the press releases was talking about opening your home's door by using Siri. So in that case, it would be abusing the access control of your house because the voice interface is not properly secured. We also proposed several countermeasures or security improvements last year. We saw that there has not been a lot of improvements since last year. And today we are going to focus on the voice recognition countermeasure. We can note that the keyword personalization is available in Samsung S Voice, but not on Siri or Google Now. And then the limitation of the attack surface or the impacts, so choosing the commands that are available through the voice interface, usually it's arbitrary choices made by the editors. So the user still cannot choose which applications or which actions he wants to see available through the voice command interface. So let's talk about biometrics and try to position the voice as a biometrics in that ecosystem. So some definitions, basically biometrics is using whether physical or biological and behavioral characteristics of an individual to identify the target. And in that ecosystem, voice is considered as a behavioral biometrics. And that's quite surprising at first sight. In general, the biometrics, using biometrics involves this complex process. There is a first step, which is the enrollment. And the idea is to get some information about the user. There is a first step, which is the acquisition with the fingerprint. For example, it's the reading the fingerprint on the reader physically. Then there is some signal processing, and an important step is the feature extraction. This step reduces the amount of information that is acquired in the acquisition phase in order to only focus on information that we think is relevant for performing the identification or the authentication. And then there is a model creation or a template creation. And after this phase, it is possible to consider the application phase. For the authentication, it's the authentication itself. And it involves the same steps. So there is the acquisition, the signal processing, extracting the features again, and then there is a comparison or a decision metrics that is involved in order to choose whether we authenticate or we do not authenticate the user. For voice biometrics, there are several applications. The two most used are the speaker verification, which is also called speaker authentication, but I let the question open. Is the speaker verification, can it be considered as an authentication? You guys are information security specialists, so you can decide what you think. And the other application that is widely deployed is speaker identification. The difference is that for speaker identification, you want to discriminate between several speakers. You have voice samples, and you try to identify which speaker spoke. With speaker verification, you only want to match the sample with one speaker. In that category of applications, there are two main cases: text-independent speaker verification or identification. In that case, you don't use a kind of keyword to perform the verification. So the user submits a sample containing any phrase, any sentence, and then the system has to be able to perform the authentication on that. And the second one, you have a keyword or a key phrase. It is text-dependent. And today we are going to focus on speaker verification, text-dependent speaker verification. So for voice biometrics, the acquisition device is a microphone, and then there is some signal processing for filtering out frequency components that are not useful for the feature extraction. And then several features or feature extraction processes have been proposed the last 20 years for that application. And today we are going to focus on the MFCC. And then for the comparison or the decision step, there are also several approaches. Our targets, so on the smartphones that we tested, the enrollment only involves 3 to 5 repetitions of the keyword. With those utterances of the keyword, a model is derived to represent the speaker's voice model. The literature clearly indicates that it's not really enough for applying machine learning model derivation. to use only 3 to 5 repetitions of the keyword during the enrollment phase. And then the speaker verification, as I said, is just finding a comparison metrics and the threshold to decide if the user is authenticated or not. Voice biometrics is easy to deploy, and that's one of the main advantages of the technique, because the acquisition device is already available on many devices that people already have, because you only need a microphone and an audio front end, in fact. And the other great advantage of using voice for authentication or identification is that the remote operation is possible, because infrastructures for vehiculating or transmitting voice samples, encoded voice samples, like the telephone infrastructures, are deployed for several years. So all the infrastructure is already there. But there are also a lot of disadvantages of using voice biometrics. And one of the main problems is that the voice changes over time. It changes over the day. It may change because you got flu, and it changes over the years also, and it changes with your emotion. So it's not a very reliable print. The acquisition of voice samples is also very easy. I'm speaking right now, so all of you may acquire my voice right now. The video will be on the internet, so my voice is public now. And it only requires basically a microphone for acquiring the voice. You can also place phone calls to the target. The tools for generating voice samples, audio voice samples, and to modify, edit those samples are available freely and very powerful. And also, one important point is that to submit your samples, your test samples, you don't need to manufacture a fake finger, for example. You only need a speaker and an audio software. And the last question is the liveness detection, to be able to discriminate whether it's a real physical speaker submitting the sample or if it's a sample played from an electronic device. That's a hard problem. In 2003, a paper was published to inform the community that there is no reliable scientific process to uniquely characterize a person's voice. So the first problem is, are we sure that the voice is unique? And then the second problem is, do we have metrics? Did we identify features that allow to extract the information that represents those unique features? And in that paper, they also emphasized that the main difficulties, it's very hard to rely on the voice for identifying a speaker, especially when the speaker does not cooperate. So when we think about a malicious, someone trying to circumvent a voice authentication, the speaker does not clearly cooperate. When there is no control over the recording equipment, because the frequency response and the filtering stages are different, depending on the audio front end, so that's a big problem. When the recording conditions are not known because of the noise, because of the possible presence of several people speaking at the same time, and especially when we don't know if someone is disguising his voice. So in 2003, they said, Okay, it could work, but it's hard to have a reliable solution based on voice. Since then, many research is focused about finding features and processes to extract the features, and then constructing models using neural networks, for example, to best represent the speaker. About the reliability issues, it's not new. For several decades, we know that the voice among the different biometric solutions may be considered as one of the less efficient. But it has a high acceptability rate, so people are ready to allow editors to use their voice for authentication. And as we can see, it was already identified that it has a high potential for circumvention.
Thank you, Jose. Okay, so even if there are many issues in using voice authentication system, then they have been implemented in modern electronic devices. And what we're going to discuss now is how can we model the voice and how we can start from the brain and to be able to have a computer model of the voice. Though, just to remember how it works, we have the airstream going up, and we have the vibrating vocal folds, then which is considered as the source, like a transceiver, RF transceiver. And we have the vocal tract, which is can be modeled as a filter, and we have the output sound. So there is a very nice reference here that you can have a look at in order to better understand how the voice production is working. So now we're going to discuss how we can characterize what we really hear when we are speaking. Voice has some very specific characteristics. Basically, it's a non-stationary signal, so we cannot apply all classical signal processing tools. The characteristics of the voice is evolving along his lifetime, so we have also to cope up with this. There is also another very important thing to remember. It's basically that the human hearing response is not linear with regard to the working frequency. So basically, we also have to remember that the human hearing is less sensitive above 1 kilohertz. So we need also to understand where the important features are in the spectrum and how we can extract those features. And that's what we're going to discuss specifically. So there are some classical signal processing tools. So we have the linear prediction substrate coefficients, which basically allows for measuring the energy values linearly using some a specific filter bank. This tool is dedicated to mimic the human speech production. So basically, we are characterizing the emission part. Then we have the discrete wavelet transform. So this tool is based on the decomposition of the higher frequency and the lower frequencies. And then we iteratively separate the low frequencies and the high frequencies on the low frequencies part only. So basically, we consider that the full characteristics of the voice is in the low frequency part of the audio signal. Unfortunately, there are some important characteristics in the higher frequency range. So basically, the second tool using the wavelet transform is the wavelet packet decomposition system. So basically, in this signal processing tool, we further split the higher and the lower frequencies iteratively. And then we extract some specific features related to the energy content in the signal. Yep. Then we have the well-known male frequency substrate coefficients, so well-known for guys working in audio signal processing area. So basically, we are not using linearly spaced filters, but we are using logarithmic decomposition just to come with the fact that there are some important information in the higher frequency range. This tool is dedicated to model the human system receiving part. So basically, how we hear the voice and not how we produce it. This tool is also easier to implement, and that's why we think that this tool is the one implemented in the target system we have studied. It's used for voice-to-text and voice recognition tools. So basically, we can recognize words in the audio signal with the MFCC and also recognize the speaker. We have seen that it's widely used for feature extraction. We have seen many papers published with this tool, like papers published by Google research teams. So we have decided to have a look on this tool and try to see if it's really contains the characteristic of the voice. So the male frequency substrate coefficient is working like that. We have a first pre-processing part in order to cope with the non-linear response of the hearing. And then we apply the feature extraction. So we take the audio signal, we decompose it into frames, and so it's a time window. After windowing, then we convert them from the time domain to the frequency domain with the discrete Fourier transform. And for doing this, we need to consider the signal as stationary or quasi-stationary. So we apply a small overlap between the decomposed frames. Then we apply the filters generated by the male scale. I think you don't hear. Yeah, it's okay. How we can? So we apply the filters in the logarithmic space. Applying the discrete Fourier transform, we are in the dB area. So we have to switch back to the linear area by applying a transformation back. We are now in the normal frequency scale, and the signal is linear. So we come back to the time domain. So we take the coefficient and apply a discrete cosine transform to be in the time domain with a linear signal. So we have matrices of coefficients that contain the feature of the voice we are analyzing. And that's the main idea behind it. Basically taking a wave file and having at the end a matrix of coefficients that reflect what was contained in the wave file signal. So once we have the MFCC analysis, we wanted to check if the MFCC is containing the audio characteristics, so the main audio characteristics, and try to test them against some well-known authentication engines. So in our approach, we consider all targets as black box systems. We don't have any idea of how they are working. We use publicly available toolsets. So basically, we went on the internet and tried to find signal processing tools available for playing with audio files. Once we want to come up with test scenarios, we had to check. We have to check if we have some important parameters. So basically, to know if the attacker knows the target language, if he knows the target keyword, and if he possesses target voice samples. So that's for the attacker profile. We need to know if he has those information. We define an experimental setup. So like every year, we propose you the setup we have designed. So basically, the main targets were running Siri, S-Voice, and Google Now. We have a computer with very nice speakers, and we submit audio samples. We provide those devices with an internet connection so that if they need to have access to the remote server, then they are able to send WAV files and have the commands we wanted to execute on them processed. So here are the scenarios. The first one is the speaker impersonation. So basically, the attacker hears how the target is speaking, and then he tries to impersonate the target's voice. So we are not professional impersonators, but we succeeded to authenticate on our phones with less than 15 attempts. So it shows that basically, even if you don't have the same voice, you may have seen that this morning, we were able to authenticate on our phones together. Just the second scenario, it's a replay attack. So we were able to record the target's voice when he's authenticating on his smartphones. So that's the last demo we presented last year. So it was the bonus of last year against Google Now, trusted voice service. So from this, we decided to derive additional tests. So if we have the legit user voice sample, we tested it against smartphones, and we wanted to check the boundaries of those systems. So we wanted to have information about how the target is working and processing voice samples. So we modified the legit user voice sample with filters. So we modified the pitch, changed the time scale, we added noise. So we have been working on the signal-to-noise ratio. And interestingly, we have seen that one of the targets, Siri, the model is shifting pre-authentication. So basically, by submitting the same sample again and again, we were able to authenticate against Apple devices. That was the first result. So if we wanted to have the boundaries about Siri, we were not able to do that because the model is shifting. So as the model is shifting, the attacker knows the keyword. The model is updated for each submitted sample. It doesn't require an additional authentication system, so whether the PIN or the fingerprint. And we just have to submit it again and again until the system is triggering. Here you have some results. So we asked our colleagues to pronounce the keyword, and we wanted to check how much try we had to submit to the device until the system is authenticated the new voice. So we have two scenarios. The first one is the legit user is using 10 times Siri, so that the model is learning from the legit user. The try number 2 is we use it 50 times. And we also, so we estimated the number of tries required to trigger the target's smartphone, so Siri. You have the number of tries required for each voice of our colleagues. And also, we have seen that the legit user is no more able to authenticate on his own smartphone. So it's a very basic denial of service against Siri.
Yeah, as the model shifts, at a certain point, it doesn't consider the initial model issued by the enrollment. So the reference is not the legitimate user's voice anymore, as you can make it shift until it accepts your voice.
Then the next scenario is the time domain reconstruction. So the attacker knows the keyword. He has recording of the target voice. So he just have to recompose a new waveform by extracting the phonemes related to the keyword he wants to construct. So here we have the first demo of the day to show you how it's work.
Ouais. Okay, so for that demo, the iPhone here was enrolled with CHAOUKI's voice. And I made him pronounce a long sentence. And I extracted the phonemes corresponding to the Hey Siri French version, so it's D Siri. And using Audacity, I just chopped the sample, extracted the phonemes, and I reconstructed the D Siri from the phonemes extracted in the sentence. We don't hear anything. We have to do it again. Oh yeah, thank you, I heard that.
Voulez-vous dire José?
Oui. Oui.
Okay.
Vous répondez.
Dis Siri.
Okay, so that's the sample that corresponds to the reconstructed time domain sample. And then just for fun, when Siri does not recognize the voice, it doesn't pop. So when we get Siri responding, we already passed the authentication. And now, just for fun, for the rest of the demonstration, we are going to interact with Siri with our own voice. The authentication is only performed on the keyword. So any user can issue commands when the authentication step is passed. And we are going to ask to send a text message to my phone number, and we are going to see how Siri responds.
Envoyez bonjour à José.
Voulez-vous dire José?
Oui. Oui.
Vous répondez bonjour.
Envoyez.
Est-ce que j'envoie?
Envoyez.
Vous devez d'abord déverrouiller votre iPhone.
So here, Siri says that to send the text message, first you need to authenticate by using the PIN code to send the text message.
C'est fait.
But he sends it anyway.
Then we switch back to the frequency domain reconstruction. So we used our MFCC coefficients, and so the attacker knows the MFCC features of the target, pronouncing the keyword. He can modify the MFCC and reconstruct several time domain samples from the feature. So we wanted to check if the MFCC were containing enough information to pass the authentication engines. So we used the MFCC inverse function of the legit user voice, and we also tested the MFCC inverse of a composition of samples. You will understand why we tested this. And we have seen that target 2 and target 3, so S-Voice and Google Now, against those systems, we were able to authenticate against those systems. So we have now another video to show you.
Okay, so what you need to understand here is that when we extract the features, the MFCC, we lose information about the time domain sample. And the inverse MFCC allows to reconstruct the time domain sample by adding noise for filling the gaps. So what we will hear in this video is, so the target is my phone, so it's the LG Nexus 5X using Google Now. On Google Now, you can define a trusted voice setting that allows you to unlock the phone by using your voice. And here, the sample that you will hear is modified. We recorded my voice. We extracted the MFCC. We did the inverse MFCC, and we played that. Where am I? Okay, we see that the phone is unlocked. So the authentication was a success.
So thanks to this scenario, we have this test. We have seen that basically the MFCC seems to contain enough information to authenticate against Google Now and Samsung S Voice, and we will discuss how we can use this in the next test. There is also the keyword composition, so the attacker knows the keyword. And what he can do is basically going into to see all his friends and ask them to spell the keyword, so to say the keyword. And what we tested basically is to superimpose all those audio samples, and we tested them against the voice recognition engines. And here are the results. So we have on the left the on-road voice. So we asked for 10 colleagues audio samples. We did the enrollment. And so we did a combination of all the other voice. So that's why you have gray space here. So we extract the on-road signal of the composition so that it's a real composition of third user audio samples. And you can see in green that the composition allows for triggering, allows for authenticating against, in that case, it was S-Voice. In orange, we have seen that we needed from 2 to 100 try to authenticate. And we had one girl's audio sample, so it's number 10. And we have seen that the composition of all the other colleagues' audio samples, with that signal, we were not able to authenticate on the device. So here we have another demonstration of that.
So here the target is a Samsung Galaxy S6 phone running S-Voice. S-Voice is like Siri. If it doesn't recognize your voice, it doesn't pop. So when we see S-Voice popping, we pass the authentication. And the sample that is played is a sample that is composed by several superimposed voices, so all our colleagues' voices. And of course, the sample does not contain the legitimate user's voice, because it would be cheating.
Siri.
So you hear the composite voice sample.
Appelez 112.
And we try to place a call to the emergency number. And that works. So we pass the authentication by using randomly selected voices of other users to pass the authentication on S-Voice. And as the models are not known from us, we don't know why it works. It's a kind of a black magic for us. We don't understand that.
One of the hypotheses we have, it's basically that as we generate all the frequency spectrum content and an overcharge of all those parameters that are required to authenticate, the system is triggered by detecting the one he is looking for. We also try to reduce the complexity for generating, so authenticating against S-Voice, and we removed iteratively audio samples of some colleagues, so which we can see here with a dark, with the dark color. And basically, we have seen that again we were able to trigger the voice engine and to command the smartphones. So just for summarizing all the tests we have done against Siri, S-Voice, and Google Now in their latest version, so that's what we wanted also to tell you. It's basically all the devices we had were up to date. So we tested the impersonation, the replay attack, the time domain reconstruction, frequency domain reconstruction, keyword composition, and we also detected that there were some model shifting issue on Siri. And concerning the target 2, so S-Voice and Google Now, we were not able to detect any model shifting pre-authentication, just because maybe we did not submit enough sample try.
Yeah, it's kind of easy to notice if the model shifts, but if you don't notice anything, it doesn't mean that it does not shift. So we couldn't conclude about the target 2 and 3. So a quick conclusion and a few thoughts. Voice interface is getting widespread, as I said, and the commands and actions that are available through this interface are getting richer and more critical. And we thought that voice authentication would be an interesting way to add a security layer to secure the voice interfaces. But as we saw in our tests, it's still inefficient and maybe immature. And unfortunately, it might contribute to give the user a false, wrong security feeling. However, the results that we presented here cannot be generalized because they depend on many factors. First, the user's language and the language diversity and complexity. It depends also on the keyword that was chosen for the authentication system. It depends on the user voice that we used for the enrollment phases during our tests. So our results work in our test cases, but we cannot really generalize the results to any situation or case. And most importantly, we don't know the model that is used to, we don't know the features that are really used. We don't know anything about the systems that we tested. And we don't know how the model is derived and how the decision is made, the comparison and so on. And maybe the model changes. Maybe it's updated during the tests, for example. Maybe it continuously learns. Sorry. Maybe it shifts, as we saw for the tests with Siri. Those systems cannot be considered as deterministic oracles that we can just request and test to see how they work. They are living beings. They change in time. That's why it was hard to provide statistics and unmeaningful. Some interesting countermeasures can be considered for the voice authentication layer. Google, for example, when you have a failed attempt with the voice authentication, it doesn't accept any other attempt, and you need to authenticate by another way. So that's a good way to prevent the brute force or doing those tests on someone else's phone. Some researchers try to prove that the voice sample originates from a user and not from a machine. That's kind of hard. But several propositions or proposals consider using the sensors embedded in the phones to whether detect the electromagnetic field of a speaker nearby the phone, or to detect the vibrations of the cheek and the head of the human speaker when he says the command. Adding entropy and interaction in the process, maybe some kind of challenge response, would force the attacker to hear the challenge and to force the response in a short time. To be able to adapt to the challenge, so it would be a good idea. And some people also think about enhancing the user's voice model. So we saw that 3 to 5 samples during the enrollment may be not enough to build a reliable model of the user's voice. And there is an interesting patent we found from Qualcomm, and their proposal is to continuously update the model while you use your phone during phone calls. So the patent strategy is to record all your phone calls and use your voice continuously to update the model. So it might you might come up with a more reliable model, but also all your phone calls go to a third-party actor. One test we didn't have time to run. Oh, okay, so we finished. We thought that as extracting features reduces the complexity of the sample that is submitted to the authentication system, maybe it also reduces the kind of brute force complexity. So maybe it would be interesting to work on extracting the features from the sample, maybe take a look at the distribution of the features for a specific keyword in a specific language, and try to estimate the complexity of a brute force on the features, and then reconstruct a time domain sample using the brute forced features. And it would be an interesting question to know how many attempts you would need to have a good probability to unlock, to bypass an authentication system. So that's a test that we would like to add in our test summary, but we didn't achieve that part. We also have open questions. It's not really our research domain, so it's a research domain that this topic is researched for more than 20 years. And I guess that some people are qualified to answer those questions. These are open questions that we ask ourselves.
Yeah, just to finish and to give you some thoughts you can take with you. Basically, we have seen that some comments on the internet about using Siri, as you have to to enter your PIN after asking for some commands. It shows that there is a real trade-off between the usability versus the security. So how we can handle this issue. And we got a very interesting response to our responsible disclosure to Apple. We told them that basically the model was shifting pre-authentication. They told us that the voice recognition system is not a security feature, and also that there is no security issue even if the legit user template is shifting pre-authentication. So that's something interesting we got from Apple. Another interesting thing, basically, if you are using unsecure system, then do you consent basically that a third party can use it? So again, this is something we have seen after the Burger King event. So let's think about that like your Wi-Fi network. If you don't secure it, then it is your responsibility if someone else is using your network. So is this the case again? And thank you very much for your attention. We thank the manufacturers and editors for their feedback. Here are the references, so just have a look at them. And if you have questions, just send us emails. And again, voice authentication is something that we will see in many areas. We have seen on this discussion on Twitter between HSBC and a guy asking them how can he modify his voice after he thinks the voice has been compromised in public areas. So have a look at this, and if you want to work on that, just contact us. We are very happy to discuss things. So thank you very much.
Thank you.
Good.